So after those two talks, I won't be talking much about the details of the CMATs, but mostly on the integration and different applications that come actually, especially with the integration aspect of CMATs. And this work is supported by NIH and the NSF in the US. So quickly, since I'll actually cover many topics, I just want to give you a map a little bit. So kind of the need for intravascular and intracardiac echo imaging. Then how we fabricate these single chip CMOS on CMOS imaging systems for forward-looking IVUS, short defabrication, characterization, and imaging results. And after that, after the baseline technology, how we can actually improve things through modeling, some excitation techniques, and also changing some fabrication materials, how we can improve the performance, which actually enables us to, for example, move to a maybe 3D ICE catheter, which will be MRI compatible, or an intravascular IVUS imaging on a guide wire, 360 micron guide wire, through integration. And actually, I added this topic for Ron, but I'm not sure he's around because he was interested in this metamaterial aspect of CMATs. So I'll just show a couple of examples of that at the very end. So motivation for intravascular ultrasound is pretty clear. Coronary heart disease is a big problem, and you have over 3 million angioplasty operations per year. And in these cases, where it's the common practice is to use X-ray angiography to find out where the blockages are. But what has been found out earlier was that even the blood may be flowing, the body keeps the lumen constant while the atherosclerosis is kind of developing. So the only way to actually to see those kind of developments is putting a probe with much higher resolution into the blood vessels, so that you can detect these things before, for example, a stroke or a heart attack. So it has proven to be an important imaging modality. So the current systems, basically you thread a catheter to the coronary arteries. You either have a single element system which sends waves perpendicular to the artery and it rotates, or you have a phased array system with 64 elements with electronics and it comes out with 8 cables. In all cases, there's actually the first thing that the operator does is it threads this guide wire first, and the catheter or even the angiography X-ray catheter is threaded on that guide wire. So that's why I'm just trying to make a note of that. If you can put something on the guide wire, you actually improve things a lot in terms of operation. So at the end of this imaging, what you get is this cross-sectional images where you can delineate where the blood is flowing, where the plaque is, and then where the rest of the tissue starts. And there are also some techniques on virtual histology, is, for example, one of them which can tell you about the elasticity, the fat content, and those kind of things, because that really helps the emergency of operation on that particular plaque. Is it going to burst, or it is safer? You can treat it with a drug. So you need that kind of information, and IVUS can provide that. But the limitation is that you only get cross-sectional images, whereas there are many cases you have total blockages of in the arteries. These are called chronic total occlusions, and basically you want to pass through that, or the other way is to the bypass operation. So if you have a good system or a reliable method of going through, then you can actually avoid bypass surgeries. And right now, actually, there are no tools to see totally volumetric images in front of the catheter to guide those type of interventions. And this is kind of the closest to a forward-looking IVUS array sold by the Volcano Corporation. But it doesn't really provide the image. It really images. It's a single element rotating system. It really constructs a cone surface rather than a full volume. So what we are trying to do is basically develop a system where you can put a ring annular array at the tip of the catheter, which can generate a full volumetric image in front of it. And it can allow a guide wire going through it. So this particular geometry seems suitable for it. So how do we kind of make these devices? Again, the challenges are, in this case, the frequencies you're talking about are 20 megahertz and above. and the elements need to be in the order of 100 micron or smaller. So you're talking about very small elements. It's pretty challenging to get electronics there. You cannot use cables. That's pretty clear. So what you can do for this connection is you can have an ASIC chip, for example. You can try to do wire bonding, which is done today for the side-looking arrays, or you can build your CMOS directly on top of the ASIC chip. Or, I mean, in several methods, we use actually sacrificial layer fabrication, as I will get into in a minute. So basically, you have very small device capacitance. So for better noise performance, small die size, and also to overall reduce connections, you may want to basically build monolithically integrated devices. And this also makes it very easy to package and reduces cost. So the way we do it is we actually design the electronics, and then we send it to a commercial CMOS foundry. We pay for it. I'll be happy to get some free CMOS somewhere, but we have to talk. And then after we get those back, we have to actually dice it. Since these are 8-inch wafers and our fabrication facilities for 4-inch wafers, we cut them down to rectangular pieces, and then we fabricate them, the CMOS on top of them. So this was our kind of the first run. Then we have another run, and we share actually these dies so that the cost is lower for us to get the full wafer fabrication. And we made actually 10 megahertz arrays and 20 megahertz arrays, and these guys have high voltage pulsers and receivers, everything integrated on those small rings. So this is how they look. Again, this 25 volt is limitation of the CMOS process that we use. It's 0.35 process, micron process. And then we have digital control, and overall power is 20 milliwatts. And this is basically when we get the chips after CMOS fabrication. This is after we fabricate our CMOS on top of it. This is after we can shape it into a donut so that it can be put at the tip of a catheter. And the number of total number of connections in this particular case is 13, and 4 of them are parallel RF channels that we read out. And we can actually, if we can say, generate DC bias levels and finalize our designs so that we don't need to control biases, this can come down to, for example, 7 or 8 connections. And on this one, we have basically 56 transmitters and 48 receivers, elements and amplifiers for them. And this is a design where we have actually a dual ring structure, so that the outside ring is our transmitter ring, the inside is the receiver ring. With that, basically, we avoid switching, and we can actually do really good electronics design for the transmitters and receivers separately to improve the performance. So just talking about the electronics. So the nice thing we had was, so this is our first design where we achieved actually 1.8 dB noise figure. And with that, we were able to measure the thermal mechanical noise of the CMOS itself. And more importantly, actually that may not be very critical, because you may have a really bad sensor with lots of noise, and you just measure the thermal mechanical noise of that sensor, no big deal. But the noise level was actually very close to the ideal radiation impedance generated noise, because we were able to bias these receivers very close to collapse, because we can do it separately for transmit and receive, and then you get a very high coupling coefficient. That also gives you a better noise performance. And once you see this noise, you can actually do even imaging and sensing on that, and this is the spurious resonances that Dr. Atala was talking about. So these devices were actually transmitting efficiently in this band, not efficiently in that band. We see it in the noise, but not in the pulse echo signals, actually. So yeah, we were able to do sensing and imaging by just listening to that thermal noise. You can do regular beamforming on the noise signals, and we'll have some applications for that. With our second run of devices, our performance was too good. We didn't want this to be too good, so we were burning power. So we reduced the power to 0.8 milliwatts in the second round of designs. Our noise level is higher, but our dynamic range is much higher. So that's kind of an ideal design for us to use. And so that we can, with small number of active channels that we use, the overall power consumption also goes down. So with these devices, we can basically image like relevant tissues. So this is a chicken heart imaged at 60 frames per second rate. And these are two cross sections, so we can basically generate video type volumetric data. The issue is processing the data, not really getting it on time to get the frame rates. And so these guys have actually more than 40 dB dynamic range. And if you look at IVUS today, that's the dynamic range that you have on the IVUS images. So that's fine and good, but this was our, I would say, proof of principle type of designs. And then you can also see other targets, relevant targets. For example, if you want to monitor stent placement, you can have your array here and you can see the stent in front of you to see how much it's expanding, which is critical, again, for the interventional cardiologist to find out if it's opposing, do they need to go back or they have to apply more pressure to the stent. You can use this array for those purposes as well. And after that, how do we integrate the catheters? So there are a couple of ways of doing that. One is you make connections at the outside and then you wrap a flex tape around, or you do through wafer vias and then you make your connections on the back side. So this is actually a device with flex tape connection. We collaborate with Aachen University to make those flex tapes for us. And we recently started collaborating with an intramural lab at NIH who are actually developing MRI compatible catheters. So they actually built a catheter for us. And that's kind of a segue to our MRI compatible imaging systems. So they're using all MRI compatible materials for the manipulation of the catheters and the catheter body itself. So right now, actually, we are testing these in terms of heating under MRI, so that's what kind of a thermal issue it will generate with those kind of conductors under MRI. So improvements. So basically, in the previous devices, we had 120 nanometer gaps between the plates. And we know that we can easily reduce them to 50 nanometers. So if you do that, you actually get 9 dB more signal from both transmit and receive. And this is achieved by actually also optimizing our pulses so that we can swing the full gap when we operate these devices. And then you can actually do simple coded excitation. And this is an example, actually it's a real signal that we tried on these arrays. And we get 11 to 14 dB improvement by just using this 13-bit coding on these things. On top of that, the isolation element that we are using between the top electrode and the bottom was a 200 nanometer thick silicon nitride, a PECVD silicon nitride, because we have to do things at low temperature. But then actually by switching to a high K dielectric, which is common, and the dielectric constant is 16 to 18, meaning that even if you put that material, it's as if it doesn't exist because it's so high dielectric constant. And the effect is more pronounced when your gaps are smaller, because then you don't add any additional gap with that material. So actually we fabricated, these are experimental results from a 100 nanometer hafnium oxide ALD layer versus 200 nanometer silicon nitride, because we can, if you make silicon nitride lower than 200 nanometers, we get pinholes and all sorts of problems. So that's actually our lower limit. But if you look at the performance, we see that in transmit, we can actually get the same pressure levels with the full gap. I mean, the maximum pressure level is constant because it's limited by the gap. Okay, so both of them get to the same maximum pressure, but this one gets there with nearly half the voltage. Okay, on receive, you basically get larger receive signal because simply your gap is smaller. You have higher transformer ratio in your device. So with that, at least, I mean, at lower voltages, we get more than 2 times improvement there. So assuming that we are electronic noise limited, that also adds another 6 dB to our current SNR. We're talking about 26 to 29 dB improvements over what you have seen in that image, basically with these stuff. So these are the devices that we are currently fabricating. Now, if you add those numbers, you can actually even do kind of ICE type of work, intracardiac imaging, at 20 megahertz with these devices. If you're interested in like surfaces and moving things, not much penetration, but you can go through in the blood for like 4 centimeters with even that tiny array. So, but then we started talking to the MRI people, and they have a need for a 3D ICE probe because they are developing interventional tools to be used under MRI. And the big advantage is that when you go under MRI, you avoid X-ray exposure, which is a problem with children, and also with long procedures. The exposure is too large even for adults. So in that case, actually, what they want was identical cross-section and geometry to the regular 1D arrays. And that's why they can use the same weave angles and they're comfortable with it. But that gives us a larger area for our arrays, so we can put more power. And it seems like with the improvements that we have, and with now large number of receive channels, we should be able to actually get a 10 centimeter field like depth with a full field of view. The challenge here is that we have to reduce the number of conductors. Although we have lots of channels, and then we cannot do kind of averaging because everything is moving really fast. So you have to get your images like 1 or 2 firings. And for that, actually, we're using lots of electronic tricks so that we can put pretty broad, use the full bandwidth of the cables to send maybe 10 ultrasound RF data in one cable itself. So that's basically a project that we started. And also another important thing is that these catheter cross-sections with small number of cables, even they will heat. So we'll have, but the thing is, we have all this 3 millimeter diameter area for us. We can actually use that for water cooling. And these guys actually have shown water-cooled catheters to be used under MRI. So when we combine those two, we may actually get an ice catheter that can be used under X-ray, obviously, but also under MRI. So again, now coming back to our real integration challenge. So we talked about all good things about IVUS, but it turns out that it's only used in 10% of the interventions, okay? And after 20 years, it is still not the mainstream clinical technology. And the biggest problem is that it's really not an in situ tool. If you ask doctors, they say, because they have to do a catheter exchange, so you have to go with one catheter, another maybe catheter for the stent, and then they need to maybe use IVUS as the third thing to find out what's going on. So also, it's an extra risk for patient. Also, the size is large. Sometimes actually you have a very narrow problem. The place you want to reach is there, but then you have a narrowing before that, and they cannot reach there because they cannot pass their catheters through. Again, I remind you that in all these things, we basically have, even for these type of intracardiac interventions, there's always a guide wire. So that's the first thing they put in. So the guide wire is used in all interventions, okay? So that's the first thing they put in, even for, as I said, diagnostic catheters. And people have done actually, have succeeded in putting sensors on those guide wires already. And so this is a St. Jude medical device with a pressure sensor, which is becoming more and more important, so they can measure blood pressure in different locations. And it has a wireless handle already, so that they avoid the cable. Now, if you look at what's inside there, that's basically a pressure sensor, but it has a 2 millimeter long rigid section, okay, that you can tap into. So now the question is, can we integrate an IVUS on that space? So it seems like the answer is yes. So the idea is that we will have actually 4 small chips in that space. And again, the challenge is that you have very small form factor, small imaging aperture, because you're talking about a very thin 400 micron thickness cable, and you cannot put too many conductors over that line because they want to use the rigidity of the wire. So the more cables you put in, they lose rigidity, and the doctors even don't like 2 cables actually added. So they choose a particular guide wire because it feels better. It slides better. So those kind of things you don't want to actually touch when you add your device. So anyway, if you can do a CMOS on CMOS single chip integration, which we had done before, you may be able to actually do that because we can do lots of integration and multiplexing the signal out. So how do we form the image? We actually put 4 of these chips, each opposing each other, but then vertically aligned, so that each one of them generates 90-degree images, and you superimpose it on top of each other to get your 360 image. And actually that's acceptable for cardiologists because in any case, whatever you do, because of the motion and everything else, they never get exactly the same cross-section anyway. And also when you're doing pullback, These guys provide exactly the same information as the regular IBUS, because you're just looking at, when you do pullback and look at the lesion length, for example, you just look at one slice, and these guys provide those slices. And the thing is, how you put it together is exactly the same way the pressure sensor is put together. They have a chip, which we just have basically 2 chips, and they're all thinned down to 50 microns and glued and all that, so it's all taken care of. They can actually put 5 cables already, combining pressure sensor and a flow sensor on a guide wire. So those things are already there for us to use. So actually we made an array already for this purpose. So this is a 300 micron by a millimeter, so exactly that size. And that's actually, this is the region, the band pads are much larger. And it has to be a small element count and higher frequencies to match the resolution that we need. So these are the initial imaging results from on-axis wire target and then off-axis wire target to show that we have the acceptance angle from these arrays. And this is the radiation pattern. And then we see that actually we have plus minus 45 degrees receptance angle from these arrays. Now the electronics. That's actually the harder part for this project. But we have actually 3 options. So if you look at here, so we have our device. We can, a couple of options. We use the 2 wires for AC power, okay? And this is AC power for better safety, so that you don't have the DC along the line. You generate your DC power here, and then you multiplex your input channels. We don't need to be fast. We only 1 channel at a time. That's the 1D array actually, what it does today. And the options are that we can do back telemetry. We can use the power lines to send back the data. We can actually do wireless transmission from the tip. So these are all different options. Actually, this is a chip that we taped out. So we'll get back in October to test. So this is the power conversion. This is digital control. These are the amplifier arrays. These are the pulsers. You can have a direct buffer, wireline output, differential hardwire output, and then ultra-wideband antenna output. For the ultra-wideband transmission, what we're doing is not a total A to D conversion, but a kind of pulse width modulation type of very 200 megahertz pulses sent out. And you look at the time difference between those pulses to get your ultrasound data. And for that to work, we had to reduce the bandwidth. So what we do is we have a 40 megahertz device, but we shift it to baseband and then sample it kind of and then send the data out to reduce the data rate. So that's what we will probably be testing in the next couple of months. But the feasibility seems there, especially just getting the output back onto the same 2 wires. So now I had this couple of slides added for Ron, but he's not around. This is about kind of these waves. We talked about these periodic structures and the metamaterials. We actually did some experiments on these kind of on that phenomena. What you see here is a 1D array that we had fabricated for some purpose. It works around 5 to 6 megahertz, and then as you see, it has these periodic membranes, square membranes. And what we do is we excite the first element, and then we detect from the last element. So we have a propagation medium in between, and we are not interested in the power pulses going out. We're interested in the waves going on the surface in this case. So if you look at that, those waves, we see that, so this is a frequency time diagram, and I think this is dead. Let me see if this, okay, so that's a frequency time diagram. We see some waves, initially arriving waves, and then some slow waves that are coming later. Actually, those are some resonant waves that we see, like those spikes in the previous graphs. And this is basically the calculation, and that's the experiment that we have done. And you also see that there's no response after a certain point. So there's a band stop kind of behavior at a certain frequency, which are very much like metamaterials. And what you can do is, if you look at the speed of sound for those waves, they actually start from the bulk wave speed of 1500 meters per second, and then they come down to 200 meters per second or so. So you can basically achieve very small wavelengths at these low frequencies, okay? Which means that actually you can start using these things for imaging. And on top of that, by changing the bias, we can actually change the frequency of these things, because we determine where the resonance is. For example, here's the stop band edge is here. If you bias it close to collapse, the stop band edge goes to lower frequency, and then you see it here as well. And this is actually comparison theory versus experiment here. I'm not sure if it's clear, but they actually match really well. So these can be used for imaging. And this is an example that came out recently where they use actually these Coke cans as resonators. It's a resonator array. And then what you can do is by using speakers outside, you can excite these slow waves on those Coke cans. And then if you do some processing, you can generate these kind of fields. Actually, if you look at the sharpness of that peak that you can move around electronically, it's lambda over 25 width. So you can do 25 times better resolution by just using those waves. And actually, we did a simulation for a CMOT version of that at 5 megahertz. This was in air, obviously. And actually, you can do similar things. This is basically one membrane. So these are boundary element nodes. So this is a single membrane. So we can focus waves, like in this case, it's lambda over 6. Meaning that at 10 megahertz, you can get 60 megahertz resolution easily. If you tune things at 10 megahertz, you can get maybe 100 megahertz resolution. Or at 100 megahertz, you can get to 1 gigahertz resolution. And again, and this is localized on the surface. So if you put cells or other things, you can actually image that electronically scanning your point rather than diffraction kind of limited resolution. So this is a possibility that we are exploring right now. So in conclusion, so the technology is suitable for IVUS and ICE in terms of performance, and it will be enabling because of this integration, a 3D ICE under MRI and the guide wire IVUS, and it really also exploring like more fundamental stuff gives us opportunities for maybe really high resolution imaging in fluids, and we can look at biosamples with that. And these are actually the senior people that I work with. 2 at Degertekin in electronics, Karim Savra is an acoustics person, Robert Lederman is actually a medical doctor at NIH, and Özgür also is a catheter expert at NIH that we work with. Thank you for your attention.
Question? So I have one. Yes. So does it would that work with Pepsi cans, or does it have to be Coke?
It depends.
That's what I'm asking.
It depends on the uniformity of the can manufacturing process. Actually, so I think it will be good for both. So I mean, it's basically what they have is with air, they couple those resonances and they get a kind of broadband slow wave. In our case, our membranes are coupled by the fluid, so the same effect happens with our resonator.
Yes.
The 10 megahertz AC power to sort of increase patient safety, would there be any challenges with that, like for MRI compatibility, or I'm just curious how you chose the 10 megahertz?
Oh, I mean, that was right now chosen as a kind of convenient number, because what happens is, actually convenience comes from this. We also use that 10 megahertz as our time base, and then we multiply that by 4 to get to 40 megahertz, our center frequency, because we multiply the output signal with that to get it to baseband, because our array works at 40 megahertz. The nice thing about that interface, it's a very generic wireless interface. Actually, we will use that for a 4 megahertz transducer. To use that for 4 megahertz, your 10 megahertz input, if you scale it down to 1 megahertz, then everything works at 4 megahertz. So that's a platform that we will start using for wireless ultrasound. But then sending kind of RF data out rather than beamform data because of the space requirements. We cannot do much in those spaces, but we can send maybe the data out.